Okay, so it's recording now. Okay, so this is pavement condition indicators. Now, we're gonna look at 4 of them, 5. There are more, I wanna be clear, but I'm gonna look at the main ones. So I'm gonna look into the deflection area basin, which is something we use for structural capacity. I think I might have talked about this one last time. I'm gonna look into cracking and rutting. This is to capture the surface damage. I'm gonna look into the International Roughness Index. This one is used for, it's a quality indicator of how smooth the ride when you drive on a pavement is. So that is the amount of vertical movement that you experience because of the damping system of your car as produced by the pavement. So if the pavement is in very good condition, you experience very little vertical variation. If the pavement is in bad condition, you experience more. And finally, we're gonna talk about pavement condition index, and I will show you one example, but there are many ways to calculate pavement condition index, okay? So we're gonna start by the most simple, which is the deflection area basin. This was proposed maybe 20 years ago. There are multiple of these, but I'm gonna look at one of them only. Now, the deflection estimated with an FWD, which is this type of vehicle, and I think I showed you something like this last time, where a loading plate will hit the pavement that will produce some deflection, and then you will have some readings. You will have some values that you will record. The machine will report this to you, and you will receive it in an Excel spreadsheet. So these deflection sensors are separated a given distance of about 300 millimeters one from the other one. And we use them to create different indicators that will relate to how strong or weak the pavement is. Now, one of them is the one you have on screen right now, which is called the deflection area basin, this one over here, okay? And if I zoom into that, the deflection area basin is looking into sensors 1, 2, and 3, which are at offsets of 300, 600, and 900 millimeters, divided by the sensor that is on the axis of symmetry, is the sensor that is 0. That sensor is exactly where the plate hit the pavement. So it's a normalization. And when the deflection is the same for D1, D2, D3, and D0, then this goes to 1, this goes to 1, this goes to 1, and this will be 1 plus 2 plus 2 plus 1, that will be 6. 6 by 6 will be 36, and that is your theoretical maximum, okay? The minimum can be something in the order of the 10 point something, 11.1, something like that. Now, it's not really an area, it is a deflection basin parameter. But for some reason, the literature call it the area. It's just the way it's called. There's another one that is called the structural number that I'm showing here at the bottom of the presentation. And the structural number uses the thickness of the pavement layers, H1, H2, and H3. It used that thickness, and it used some coefficients that are related to the strength of the layer. So for instance, for the hot mix asphalt layer, the coefficient is something like 0.3, 0.35, 0.4. For a granular base, can go as high as 0.17, could be 0.15, like in this example here. And for the sub-base is weaker, so the coefficient is smaller, typically somewhere between 0.06 to 0.10. And then you have something else that is here in the drainage, and it's a characterization of the drainage. You can assume it's 1 just for the purpose of this class. However, that is not true. We will see in pavement design what is the actual value, but this is just to show you that this is another way to characterize the strength of a pavement. In this case, for this example, the pavement will have 0.471. Values can go as high as 9. Okay, I see 5 questions. Take my time. Okay, I'm going too fast. Guys, if I'm speeding, you have to let me know. But this is just a direct equation that you put the info you have and you get a value. So this one doesn't have nothing really difficult, okay? And I believe last time I show you in ArcGIS the actual deflection values for a sample data set, and we estimated this parameter already. So
Sir, I have one question about the H. Is it pavement thickness layer?
It's the pavement thickness in inches.
Yeah, in inches. What about A1 and A2, A3? Which is
A1 is a characterization of how strong the pavement is, and is correlated to the elastic modulus of the pavement. The same is true for H2 and A3. So this is a characterization. There are charts where you can go and read.
Yeah, but from the chart we can get these numbers.
Yes, and that's something we will actually cover in pavement design, because this is one of the AASHTO pavement strength coefficients. So I don't really want to go there. I just want to tell you that this exists. Okay? If I show you quickly without you being scared, so it satisfies your question. So just give me a second. Let me see if I have the lectures for this. Okay, so A1 for the asphalt cement is between 100 and 450, A2 between 0.06 and 0.14, A3 between 0.06 and 0.14. You can put the elastic modulus and it will give you A3. You can put the elastic modulus, will give you A2, and A1 will come from this chart. In this chart, you go with the elastic modulus at the bottom. Say you have 200,000, you go hit and you read 0.3. That's the coefficient from there, okay? And there's also correlation between the CBR, the R value, modulus of resilience, and the structural coefficient A2 and the structural coefficient A3. So if you have a CBR of 33, you go here and you read a 0.10 structural coefficient, okay? So there are charts and there are equations and there are ways to estimate that. But what matters for this class is that you can characterize the strength of the pavement through the structural number, or you can characterize it with the deflection area or any similar deflection basing parameter, okay?
Thank you.
All right. Now, because I already did an example and it's just taking the numbers and punching the numbers in there, I'm not gonna give you an example. I'm actually gonna jump into cracking and rutting, where we are gonna spend some time. So the first that we're going to look is cracking, and is the surface damage indicator for the amount of cracks that a pavement might have. And there are two types. One could be fatigue cracking. It's called alligator cracking, and it's the picture on the top right. The other one is called longitudinal or top down, and it's the picture on the bottom right. We have equations to estimate that, but to estimate, we need to know what is the tensile strain in the asphalt cement layer. And we need to know what is the load and the area of application of the load from the tire of the vehicle. And we will compute the allowable number of repetitions to failure for each axle configuration and load. And we will know, because we have counting or weighting motion technology, we will know the number of axle passes that have used the road. So for instance, you will know that the road has been used so far by 300,000, 18,000 pound axles. And when you go and calculate the allowable, you know that you can have up to 1 million. So you do your 300,000 over 1 million, and that gives you 30%. So that's what we call fatigue, is what percentage of the life has been used. Now we're gonna look at the equation. Don't get scared, we're gonna do an example soon. But there are two types of equations. We have the bottom up fatigue cracking, which is typically the most important one. And in the top equation, you see that the only factor is FD, which is the fatigue damage. And the fatigue damage is coming from the actual number, n, a small case n means actual number of load applications. And let me see, where do I put this so it doesn't go in the way? And the capital N is the allowable number. And the I, J, K, L, M, it depends on the specific circumstances of the axle, the load, the weather condition, the elastic modulus of the materials as they change during different temperature and so on, okay? Now, that was bottom up. This is top down. It's very similar. If you see, it's FC, FD. The FD is exactly the same, but the FC is slightly different because considers the thickness of the asphalt cement layer. Okay, so we have to calculate a C2 prime coefficient that the only thing that we require is the thickness of the hot mix asphalt. We put it in here, and then we need the fatigue damage. The fatigue damage is again the number of observed repetitions for a given combination divided by the allowable, the maximum that we can have. And that one is given by another equation that is coming from the Asphalt Institute, which is this one. In this equation, and this equation applies to both bottom up and top down. In this equation, we have the tensile strain, the elastic modulus of the asphalt cement layer, and we have two additional coefficients, C and K1 prime. C is given by this equation on the top, and B is the binder, the asphalt cement binder percentage by volume. You can think of a 10, 11%. And VA is the volume of air on the asphalt mix. You can think of that like a 5%. And then the K1 prime depends only on the thickness of the asphalt cement layer. So we can get that value right away, okay? So we can get both values. And then you put both values. Now you only need the ET and the E. The E is the elastic modulus. So that's something you know is 100,000, 150,000 is the chart I showed you before. And ET is the tensile strain. For this tensile strain, we need to know what is the type of load that we have. Once you know that, and I will show you how to calculate the tensile strain with a simplified approach. We typically use software, but I will show you one equation that I have adjusted a little bit just for this class. Once you have that, you have an NF, and that NF will be 700,000 load repetitions. Is the maximum amount of loads that the pavement can handle. So it will be a number. Now, the ET, the tensile, can be estimated roughly with this equation you see down here. In this equation, we have nu, which is the Poisson ratio. For an asphalt cement pavement is something like 0.35. For a concrete pavement is like 0.15. We have E again, the elastic modulus. And we have Z, which is the depth at which the tensile strain is happening, okay? Now, the only problem is that this equation was created for only one set of tires, one side of the axle, and one layer of pavement only. So I have modified the equation a little bit just for the purpose of this class. That's why it's in red, so that we can calculate something approximately to what it will be. So this will give you ET. We're looking at the tensile strain, which is cracking, right? I put in here also the vertical compressive strain because that one is applicable for rutting, and we are gonna talk about rutting later in this class. So I want you to keep in your mind that we might need to use this equation as well, okay? So look at this chart here, and let's look at the one on the right-hand side. The tensile strain is happening in the interface between the hot mix asphalt or the asphalt concrete and the granular. So that is the location where we need to go and measure the depth. You see how I have a parameter called Z? Z to the power of 3, Z to the power of 2, C squared. I have Z here again. That C will be the thickness from the point of the surface all the way down to the interface between the asphalt, concrete, and the granular. So it will really be the thickness of H1. It will be the thickness of your concrete layer. It will be the same as HAC. It's exactly the same as HAC, the thickness of the asphalt cement. Now, that's the case for a traditional granular pavement. On the left, you have a full depth pavement. For the full depth pavement, the story is the same. It is the interface between the hot mix asphalt or the asphalt concrete layer, but now it will be the subgrade soil because there's no granular base. But it's the same. The Z will be the thickness of that layer, okay? Questions, guys? We're good. Otherwise, I do an example.
No, it's okay.
Professor?
Yes.
So, okay, so both are basically fatigue cracking. Can you just explain, I mean, why, like, what's the reason behind calling it top down and bottom up? I mean, like, what entails that terminology and nomenclature?
Oh, yes, because I only explained the bottom up. I didn't explain the top down. So
okay.
The bottom up, thanks, Cameron, that's a good observation. The bottom up is happening because of the tensile strain that is happening at the interface, as I said, between the layers. So when that happens, the crack starts here. Why? Because you are suffering tensile strains, right? And that produces a crack because there is no rebar, like in a regular beam. If there were rebar, the rebar will take the tensile and the crack will not propagate. But because there is no rebar or nothing, the crack will propagate all the way up. So that's why it's called bottom up. The down, sorry, you have a question?
No, I'm good.
Oh, okay. So the top down is happening because of some weather and temperature variation between the day and the night. So I'm not gonna explain that one because it's complicated. We're just gonna consider and worry for this class for the bottom up. So,
excuse me.
Yes.
Sometimes alligator cracks are without any evidence of settlement, and it seems that they are only because of the repetition of load. But there are some alligators which are formed after the settlement of the pavement. Can we name these kinds of alligators fatigue cracks either?
They are fatigue crack as well, but they are fatigue crack combined with rut depth or rutting. And
okay.
You are talking about this one. I'm just going to jump through, but you are talking about the bottom right picture. Look at the picture on the bottom right and tell me if that is what you're talking about. Okay,
exactly.
So that's a combination of fatigue cracking and rutting. It's a combination of these two. So you see this other that is called EZ. That's the compressive or vertical strain, and that one will produce a permanent deformation. And we're going to talk about that one in a little while, maybe in 30 minutes from now. But what you refer to is a combination of this tensile strain and the compressive strain, both of them. Because then this produces a deformation here, that translates here, that translates up here. And then you end up having both combined, okay?
Okay, thank you.
Yeah. So one thing that I ignored to tell you is that the fatigue damage will be calculated for every month where the moduli, elastic modulus of the base and subbase might change. It will be calculated for every axle type, for every load level. It will be calculated for the wandering of the wheels on the traffic path. And so I'm just gonna simplify it a bit, okay? To be able to do it. So we're gonna have this. We're gonna have to calculate the bottom up fatigue damage first. We will calculate cracking in a moment, but we're gonna calculate damage first. For a 6 inches thick asphalt layer, which is directly on the subgrade soil. we are going to assume that we have observed 325,000 ISAL. That means, guys, that we have a weighting motion. A weighting motion is a sensor that is embedded in the pavement. And when the vehicles drive over that sensor, the sensor will detect it and will send it into a computer that is nearby. And it will measure the weight of each axle and will accumulate. And it does this 24/7, 24 hours a day, 7 days a week. All right, so those 325,000 ISALs are coming from there. An ISAL, just one, will be 9,000 pounds of load on a dual tire single axle that has a circular imprint of about 4.5 inches radius to a maximum of 6, but we're gonna use 4.5 now. And we're gonna assume the asphalt is not very good quality. We're gonna assume is 100,000 PSI. Now you know that this value goes from 100,000 to 450,000. And we're gonna assume that the Poisson ratio for the asphalt is 0.35, okay?
Professor?
Yes.
What's the role of this Poisson ratio in this scenario? Like
Poisson ratio is the deformability in the radial direction compared to the deformability in the vertical direction of a cylinder of the material that you are testing. So the lower the Poisson ratio, the less deformable. The higher the Poisson ratio, the more deformable.
Okay.
This is a not very good quality asphalt, right? You would prefer 0.25, 0.2, 0.15 will be preferable, but I'm giving you 0.35 to inform.
Okay. Thank you.
The role exactly, you will see it in the question coming in a moment. So let me copy the info, please, first. So we have the thickness of the asphalt cement. Do you mind if I say HAC? So this is going to be 6 inches.
Yes.
And then we're going to have the elastic modulus of the asphalt cement, 100,000
Yes, sir.
pounds square inch. And we're going to have the Poisson. I'm just going to type Poisson complete, but you can put new if you want, since I don't have the mathematical symbol here. So 0.35. We have the P load, which is equals to 9,000 pounds.
Yes.
The radius equals, I'm gonna call it A, just for those of you who are in the other class, you know what I'm talking about.
Yes,
And this is gonna be 4.5 inch. The area of application is gonna be given by pi times that square, right? And the Q, which is the uniform load, that uniform load is gonna be equals to 9,000 divided by the area. So that is pounds square inch. And I have N. Now this is a small case N, so I'm gonna put a dot. It's just a trick, okay? This is equals, this is the, or maybe I do it the other way. I say observe loads. That's N. And we have observed, we say 325,000 repetitions of the 9,000, which is really 18,000 pounds per axle, which is a ISAL. I'm taking an ISAL. You guys will see this if you're taking pavement design with me, but here I'm not gonna give further explanations. Okay, I think that's all the information I have. So now I want to estimate what is my tensile strength. right? So my tensile strain is going to be 1.25, and I want to clarify again, this 125 is not part of the original equation. So this is just because the equation is created for only the axis of symmetry of the tire on one side. When you consider the other side, it typically increases between 20, 30%. That's why I'm saying 125 times 1 plus nu Poisson ratio times Q, the uniform load, divided by 2 times E. I'm going to put all this in a parenthesis, and I'm just going to click to make sure it's fine. Okay, now times, and now I'm going for what is inside the square bracket, okay? So that is 1 minus 2 times Poisson ratio minus, I'm going to put it in parentheses, 2 times 1 minus Poisson ratio times the depth. I don't have the depth. But do you guys see that the depth is the same as the thickness of the AC layer? That's what we talked before, right? So it is this one.
H.
Yeah, it's the H, exactly. Now I'm gonna divide that. I'm gonna open a parenthesis, so this is A squared plus Z squared, this is this one. And this is to the power of 0.5. Okay, guys, sorry, I'm just gonna run this a little over here to be able to see the entire thing. Okay, so I close this parenthesis and I continue plus, and now I have C cubed. So is this 1 cube divided? Just gonna do it like this, just to make sure that the cube is not being confused. That's divided by A squared plus Z squared to the power of 1.5. I cannot see how many parentheses, so I'm just gonna click on this one. Okay, it's detecting now. So that closed all the parentheses.
After 0.5, I think we need another parenthesis.
Yeah, that's exactly what I'm checking. Let's see. Because this is this, and this one was close here. You say
Yes.
here?
Yeah.
It doesn't need extra.
No, I think it's fine because this is this. And that is to the power of that. I am avoiding the division to get confused. And then is this divided by this. I think it's fine. It's apparently fine. I'm just going to remove the 125 because I know what that value is without the 125. Well, it seems more reasonable. The only thing is the tensile strain, so it's negative. Sometimes the sign it relates to whether it's compressive or tensile. So, but for the purpose of this class, we're going to use the absolute value. So I'm just going to put the absolute value here next to it. Now, that only tells me my tensile strain, right?
Yes.
I need to go and estimate the number of allowable, which is allowable is equals to NF. And you see I need K1 and C, so I'm just gonna calculate K1 and C for here. So I'm just gonna calculate those two and come back here. Oh, and I need the I need the volume of binder,
And the
and I
volume
need
of
the volume of air.
Air.
So for binder, I'm gonna use 10% maybe. And for the air, maybe a 5%. And okay, so the C will be 10 to the power of 4.84. And then it's gonna be VB divided over VB plus VA.
add another parenthesis before B14.
V14.
Mm-hmm.
No, why?
Oh, it's
In the
fine.
equation, there is minus 0.69.
Yeah.
Are we multiplying? Are we multiplying or
No,
we're
no, 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 no. Thanks, Cameron. Yes,
Yeah, no
I
problem.
need new glasses. Okay, so that looks about right now.
Then how can we calculate VB and VA? Or it's given in the exam, for example.
So you care about how you actually do it when you are professionally working, or just for the purpose of the class?
Just in the class now.
Oh, okay. So later on, you don't care. So for the class, I give it to you.
Okay, thank
Do
you.
you want to know what happens when you are, or can I ask you, where do you think this comes when you are working professionally in a company?
Yeah, I need to know that.
So can you tell me?
Me?
Yes.
Mm, I think there's something on specific gravity or something like that to know the volumes.
You have a laboratory, right? And
Yeah, we have to test it.
Yes.
yes. So you have to test for the quality of the mix that you are doing. So you take a sample and you know how much binder and how much volume of airs. So you do some laboratory test.
Okay.
Okay, let's go
We
for
had
this
in
one.
soil mechanic, I think that we could assume the volume of air in the soil, I think.
But this is not on the, yes, I know what you're telling me, but this is not on the soil. This is on the hot mix asphalt mix. It's on the mix. So when you are creating that mix, you know how much binder you have added by volume, by weight. But then by volume, you take a sample, right? And out of that sample, you run some experiment that will tell you this amount. The K1,
Sorry, this binder is bitumen.
yes, of course.
This
This is
is
asphalt
the
binder.
volume of bitumen.
It's asphalt binder, yes, it's bitumen.
Okay.
And this is air.
Okay. Thanks.
So the K1 only depends on the thickness, you see? So that one should be very simple. And I'm only gonna do the bottom up. I'm gonna ignore this equation, which is top down. So I'm only gonna do this one. Guys, correct me if I made a mistake, please. So 1 over 0.000398 plus 0.003602 divided all that by 1 plus the exponential of 1102 minus 349 times P1. Okay, it looks to be fine. So I can go back now to NF. So my NF is going to be 0.0032 times Q1. Oh, sorry, I forgot the equals here. Times C. times. And now I have 1 over the tensile strain. To the power of 39492. And now I have 1 over the elastic modulus to the power of 1.281. Just trying to check here. This close here. And it's to the power I close here. And I need another parenthesis probably here. Okay. I think that should be right. Okay, 1 prime C. Okay. I'm getting a rather large number. Okay, let me just check quickly, guys. This is...
I think the C is different from the value in the presentation.
Yes, I'm getting slightly different values for everything, actually. I think in the presentation I use different, maybe I use 11% here, but that's not going to change much. What is the key one in the presentation? Oh, I have it here, right? Oh, the C is completely different. So something is wrong on this C. The K1 is 250, so that should be about right. Yeah, so the K1 is fine, but the C, something might be wrong, the C. Ah, I know. I think I know because I wrote this in percentages. Give me a second, please.
Sir, you should put in the decimal, I think.
Yes. That's exactly the case. Thank you very much. But it's not responding. Format. There's something wrong with this C. Or maybe I multiply when I was doing that one. Maybe I made a mistake and multiply. I know it's minus, I know.
Sir, it needs before B14, I think it's one more parenthesis.
Here?
Yeah. And after that, close it at the end.
Think that, yes.
Yeah, and at the end, after the here. Now that's gonna be fine.
Ah, thank you.
You're very welcome.
Yeah, now it looks a little bit more reasonable.
Yes.
I'm gonna remove the decimals for this. And maybe we put the comma for thousands, so it's easier to interpret. So I have a 49 million repetitions allowable for this. Of course, this is for one of the, this is for a 9,000 pound, right?
Mhm.
So if I know my area of contact is different, this is gonna adjust automatically. The same if I know the load is now the 9,000, but it's maybe at 12,000. So depending on the load and the area of application, also the material property, right? If this is a 150,000, it's gonna increase. The thickness of the layer. If the thickness changes, the material capacity the material capacity is gonna change. But for this one in particular, I have 15, almost 16 million, and I have observed only 325,000 repetitions. I think the one that I posted is incorrect because I probably multiplied when I was calculating this. So this is probably wrong. So I think rather put this one instead. And also this is 9,000. Yeah, I think I made a mistake here in this 0.01 in this C value. I probably made a mistake there. Okay, so now we will look into the ratio. But look, this is a summation, right? And we are only looking at one specific axle. So there are other axles, but when we look at the ratio, this will be 325,000 divided over 49 million. And this will be, we can put it in percentage, maybe to visualize better. Okay, so it has consumed very little of the life of this pavement. This will be my fatigue damage. If I know that more vehicles have used the road and now we're looking at maybe 15 million, then the ratio of fatigue damage will increase. So it's fully dependent on the amount that I have, right? That's why this is the small case N and this is the capital N. So these two numbers are very important. This one you calculate, this one you observe. So the accuracy which you observe this is really important for the estimation of the fatigue damage. You will go with another axle load and estimate exactly the same and observe how many you have out of that one. And then you will start accumulating, right? So you will go something like this. You will know your load is 9,000. You have another one that is 10,000. You have another one that is 11,000. You have another one that is 12,000 and so on. And for each of them, you know what is the number of repetitions and what is the number of allowable, right? So for each, you know N, and in this case, my N here was 325,000 for this one. And that gives me an allowable of 49,655 million. If your load increased to 10,000 and you have maybe 1.5 million, then you know that you have that amount and the allowable is this one. Then you go with 11,000. And you count how many of those you have. And finally you go. So you have to, the idea, what I'm trying to do now is to just tell you, you have to repeat this over and over with the different loads that you have. Okay?
So, Professor,
Yes.
My understanding is, so essentially, basically, we are just calculating those Ni, Nj, Nk, all those observations, right? How you have in the equation, the fatigue damage, summation of basically I to M.
We are calculating the fatigue damage, and we're calculating this I, J, K, and
all
M.
those
We're only,
N, I, J, K
yes,
element, right?
but no. Yes and no. We're doing that.
Okay.
Cameron, just a moment, please.
Yeah.
We're doing it, you are correct, only for only for different load level. This is the only variable I'm changing now, load level.
Load level, okay.
Because you will have the elastic modulus that may be different during summer or winter. Okay. So you have to break it also per time. And so you will have specific circumstances that are gonna change this. And also,
I see. Okay.
I'm putting all the vehicles passing by the same point, but when you have the vehicles driving, they kind of wander on the width of the lane. So it's just a percentage that goes, and it's like normally distributed. Not sure if you're following what I'm trying to picture, but this, not all the vehicles will drive over this. Some vehicles will be here, other vehicles may be here. It's like a 70%, it's a percentage, it's a probabilistic distribution. So we still need to multiply that and concentrate it. So I'm making an oversimplification so you understand. That is difficult to estimate this thing. It takes time. Okay.
So in this example, you are basically just changing the loading, the axle load. So, I mean, in reality, are we just taking basically the worst case axle loading if we are calculating fatigue damage for particular pavement?
It's like
say,
this.
Whatever weather or
Look
conditions.
at the table.
Yeah.
This is a little more realistic, but this takes like 1 day of work to estimate this. I cannot do this during this class, but you will have the different seasons of the year, and the modulus of elasticity is going to change. And then you will have the amount of load that will change as well. And that produce different tensile stresses. And then you have that distributed in different axle types, tandem, single, tridem. And then you end up with your allowable observed, and then you end up with a consumption of life, and then you have to add them all. And once you have added them all, then you start estimating your damage, and from damage you estimate the cracking, and the cracking accumulates as time goes by in percentages. Okay, but it's complicated. So I'm just doing one to illustrate the approach here, and so you understand what is behind when we say what is cracking.
Okay, thank you.
It's not like a closed form, and this goes to everybody. It's not like a closed form like we had before, guys. That before you just had this equation and the equation, you just put the values and that's it. No. In this case, for this, you have the fatigue damage just so far now here with a percentage. And once you know the percentage, you still have to put it in this equation and get the cracking from the equation. And so I just put three loads, but you will have much more than that. So I'm just gonna go back to the presentation here. And okay, so now you have a better idea what's happening. So the NF gives you the total, and then you have the amount that is observed. Now let's look at what happened when we know the fatigue damage, and how do we take the fatigue damage to the cracking, okay? to take fatigue damage into cracking, we need to estimate this C2 prime, which is based on HAC. And once you have estimated that, you get the C2 prime value. In this case, for instance, is minus 2.5. And this is for a specific circumstance, right? So I'm assuming that I have a 6 inches asphalt layer and that I have a 10% bottom-up fatigue damage. So I put my fatigue damage here, and that will tell me my fatigue cracking, okay? So a fatigue damage that is 10% gives me a fatigue cracking of 7%, roughly. And if I plot multiple of them, right? If I plot multiple fatigue damage versus fatigue cracking, you can see here the relationship. This is for a 2 inches, 4 inches, and 10 inches layers. They all go up in a similar way. The 100% fatigue damage is a 50% fatigue area. In the old days, 20% fatigue crack was the end of the lifespan criteria for cracking. And that corresponds to fatigue damage of about 40%, roughly speaking. It depends on the thickness, you see. It's not the same for all thickness. But this is how we know how cracked the pavement surface is. So when we reach a given percentage, and the AASHTO recommends a 20% fatigue crack, then this layer is gone. It's time to put a new layer. If you have less than 20% fatigue crack, then you can still do different things. You can do crack sealing, or you can do microsurfacing, or you can do hard in place recycle or mill and overlay, but not the entire thing. So you can do stuff. There is another indicator that is called rutting. The rutting can be seen in this picture. Let's start by the top left picture. It is roughly where the majority of the trucks drive. And it is a permanent deformation that the pavement will not recover. In the top left is not accompanied by the crack, because the pavement, the compressive strain was possibly high and produced this over time. It's the accumulation of damage. In the bottom right is combined with the cracking, with the fatigue cracking. Now, the plastic deformation, which in popular words is called rutting or rut depth, this plastic deformation is computed based on this equation. You multiply the plastic strain by the thickness of the layer that produced that plastic strain. So you have to do it for the different layers that you have in your asphalt. Sometimes we have two. That's the most common case. We have the asphalt base and the asphalt layer. But if you have granular, you will have to add the granular layers as well in here, base and sub-base. Now, this EP, because the H is very easy, is the thickness. So is your 6 inches than the case before. So you know what is that thickness. The EP, the plastic strain, is the one we don't know. That plastic strain can be calculated as a ratio of the elastic strain with these values, where K1 is a constant, T is the temperature, and N is the accumulated repetitions of load. And EV is the vertical elastic strain. So this vertical elastic strain is the one I showed you before. Is this EC? This is your vertical elastic strain. Now, again, guys, this is an approximate equation, okay? just for the purpose of this class. Typically, we have to go in software, and the software will give us that. So the K1, you see we have K1 here, right? K1, T and N. So the K1 is given by C1 plus C2 times the depth at which we're interested, multiplied by that to the power of the depth. The C1 is a function of the thickness of the hot mix asphalt layer, the asphalt cement layer. The C2 is a function of the thickness of the asphalt layer. And the depth is the depth at which you are interested. Now, at what depth are you interested for rutting? The rutting, if you are in a granular pavement, is happening at the contact between the subgrade soil and the granular base. But that will be the rutting for this granular base. There's another one that could be happening here at the interface between the asphalt and the granular, okay? So those are the depths. Okay, so that is the depth. So if we're talking about a 6 inches, we will use 6 inches. But if there's a granular base, we will go and use again the granular base. So we will estimate that 2 times because we need to estimate 2 plastic strains. So let's look at an example. We want to compute and plot the plastic strain. Plastic strain is this EP, and EP is coming from this equation, okay? And we're gonna do it at the mid depth of the asphalt cement just for fun. And this is gonna have 6 inches. The temperature is gonna be 85, so it's gonna be a hot day. And we're gonna look at 1, 10, 100, and 1,000 load cycles, just for fun, just so we understand how this works. And we're gonna calculate the plastic deformation after the 1,000 load cycles. The elastic vertical strain will come from that equation, but I assume you guys don't want me to run into troubles again in Excel, although we can do it if you wish. So we're gonna assume that it's giving us 5.7 times 10 to the power 5. I'm just gonna show you here quickly. I think I have the rutting yes here. I'm just gonna show you that that's a reasonable value. So this is 1 to the power of minus 4. And this will be 4 to the power of minus 4. This will be 2 to the power of minus 4. And we're using a 5 to the power of minus 5. So it's somewhat a small value. It's not that big, okay? It's like a 10% of what you typically will get. Okay, let's see. So we have my temperature is 85. And the thickness of the layer is 6. And the loads, well, I'd be interested in several of them, but the 1,000 is like the maximum. This is my end, right? And the elastic strain is going to be 5.7 times 10 to the minus 5. Yeah. So I'm going to estimate the K1. I need C1. I need C2. So C2 is going to be 0.0172 times the thickness squared minus 1.733 times the thickness plus 27.428. And C1 will be minus 0.1039 times the thickness squared just gonna put it like that to make sure that it's not gonna give me error. 4868 times the thickness minus 17,342. And this one is C1 plus C2 times the depth. Now, I recommended the depth to be halfway through, so I'm gonna put it here, depth. So we can play with that. So for now, I'm saying is at halfway. So I'm saying that divided by 2. So let me just go again here. So this is C1 plus C2 times the depth times 0.328196 to the power of the depth. So that's my K1. And I need to go now back into this one and use this equation. So my EP, or my plastic strain, it will be K1 multiplied by 10 to the power of minus 34488 times the temperature to the power of 15606 times the number of loads, let's start with 1000, to the power of 0.479244. So the plastic strain is 16. Ow. This is multiplied, sorry, by the elastic strain. Sorry, this is not a value by itself. I have to say equals, apparently. Yeah. No, why? This is it. So hold on a second, guys, sorry. So it's 57 to the power of minus 5. So it's that. So that's my plastic strain. And, right, so if I know the thickness, I can go to the previous, which is here, and I can say my permanent or plastic deformation is simply the multiplication of the plastic strain by the thickness of that layer. And this will be in inches, right?
Yes.
Now, I use 1000 load cycles, right? If I increase the number of load cycles, then it's gonna be more. If I say 1000, then that's gonna increase. If I put less, then it's gonna be much less. So there will be a relationship between that, the more load cycles, and these are accumulated load cycles. So we can put it here in centimeters if you prefer, so we have a better feeling for that. Or millimeters, maybe it's better. So it's 0.1 millimeter, okay? So far that's not an issue. It will become an issue the end of life in AASHTO is 12.7 millimeters. From a Rutting perspective. So I can even estimate how many do I need. So let's try with 10,000. Okay, I'm almost there. Okay, let's say it's almost there. So I need 11 million. $11 million loads to reach the end of life for this hypothetical case. Do you guys realize that this elastic strain is coming from the similar analysis as we did before, where you have the amount of load of the axle and the area of application and so on and so forth. So it's similar to this. Like in this one, we actually estimated what was the tensile strain. This was a 3 to the power of minus 4. In this one, we didn't estimate the plastic strain, the elastic strain. We actually took it for granted, given by us from another analysis. Yes, go ahead.
And does the time period of applying these load cycles matters at all?
No.
No?
No, because this is an instantaneous application of load. The elastic strain is just an instantaneous application of load. It's just an instant that the vehicle with the amount of load passed by that specific point of the pavement.
Mm-hmm. Mm-hmm. Okay.
But with time, it becomes permanent damage. It accumulates with time.
Mm-hmm. But in our calculations, we didn't basically apply any factor related to time.
Yes, these 11 million loads are accumulated through time.
Okay, which time? What is the duration of time? It's a year, it's a, I don't know, 10 years.
You need to calculate how many of these you have per year. So if, for instance, imagine you have per year, or you have, let's say it this way. You have on the base year, 750,000 of those loads. And you have a growth rate 2%. So let's say after 15 years, you will have that's going to give me an error. I know. I need to just type the 15. So, but I'm creating an accumulation factor.
Okay.
It's going to give an error, I know. So after 15 years, you have 17 times as accumulation factor. So after 15 years, you will have decimal, sorry. $12,970,000 in 15 years. So I say 11 million, so it's a little less than that. So maybe 14 years.
And do we have a rough estimation for a brand new, basically pavement, about its lifespan? How long does it take to be damaged? Or it's really basically dependent on material or the environment or all this together?
It depends on many things, and you need to attend my other class for that. We're gonna look at that.
Oh, okay.
But in this one, I need you to understand, because we're gonna create a performance curve for rutting. And we're gonna say the rutting is gonna progress in this speed. So I will not look into these equations anymore, but I need you guys to understand where is this coming from.
Oh,
And also that is not that simple, it's complicated, as you see, estimating rutting and estimating cracking. Actually, rutting is, I haven't finished. This is only the rutting on the asphalt cement layer, this one so far.
Exactly.
So this is only asphalt cement layer. There is rutting in the other layers. this is how the number of cycles and the plastic strain will move.
Mhm.
But as I was saying, there is also rutting in the granular layers.
Yeah.
Go ahead.
I don't have any question.
Okay. So we have a similar equation. We have the plastic strain, and then we need the vertical elastic strain on the base or subbase. And N, which is the number of load cycles, is here on the power of E. And then we have a bunch of constants. Beta G, which is 167 or 135, depending if it is base or subbase. We have nu, we have rho, and we have beta, which is given here. So beta comes from the water content, and rho comes from beta. So it's also from the water content. So these two comes from water content. So it's easy to estimate beta and rho. Let me just go to the full presentation. Sorry, guys. Probably you cannot see it. So this beta G is a constant, is found down here. E0 over ER, I show you in a moment. It's on the next slide. Rho and beta are constants that depend on the water content. And N is the number of loads, repetitions, as before. And E0 over ER is given by this value, and also depends on rho and beta. So depends on the water content only of the base or subbase, okay? But how do I know what is the amount of water content on the base and subbase? Can somebody tell me? Is it fixed through time, the water content? Or does it change?
It
How much
depends on
water?
the rain.
Oh, it depends on the rain, and also depends, you are correct, thank you. And it also depends on how good the drainage is to get rid of that water. And so the rain depends then in what climatic region you are at. And that rain also depends on climate change, right? If it is gonna rain more. So there are many dependencies behind that water content. But as you can see, for the base and sub-base, the water content and the number of load repetitions are the most important two elements. If you have those two, you get everything else right away. I think I have an example, yes. So we're gonna compute plastic strain and deformation in a 10 inches thick granular base. So we're gonna assume that this was our asphalt layer and now we're working on the base. So the thickness of the base is gonna be 10 inches. The water content is gonna be assumed constant and fixed at 18%. That is not true. The number of cycles, N.
1,000.
I'm gonna put 1,000 now, but as I did in the one before, you saw me that I start playing with this, right?
Yes.
But I'm gonna start with 1,000. Compressive strain. Is that right?
No, I think you need to add one more zero.
No, it's right, I think.
Right, sir.
1, 2, 3,
6.
4, 5, 6. Yeah, I think it's right.
You're right. Okay.
We're gonna think it's only one layer of base. So base and sub-base all together. So I'm gonna get beta first. So the log of beta, the log of beta. is minus 0.6119 minus 0.17638 times the water content. Okay, let's see if this wanna do it. Okay, so that's better. I just took exponential of that. Rho, I don't have this symbol, so I'm gonna say rho, okay? But it's that rho that is here.
Yeah.
Is 10 to the 9 times minus 4.9285 divided by 1 minus 10 to the 9 to the power of beta.
Yes.
That closed the denominator, that closed the entire expression, and I have an extra power to the power of 1 over beta. And E0 over ER is, I'm just gonna write 0.5, this is here, times 0.15 exponential, sorry. Okay, is rho, let me see. Yeah, it's rho to the power of beta. Ah, I forgot the equal. So it's rho to the power of beta. Yeah. Plus 20 times exponential of, oops, now this one is rho over 10 to the 9. And then to the power of that. Okay, see, rho divided by 10 to the 9 to the power of beta. And I close the parentheses of the exponential. And I close the parentheses of the entire expression. That seems about right. Okay. And now the plastic strain. Is equals to the elastic strain. Sorry, I need to say this is elastic strain. So it's beta G. Okay, so I have 167 for base and 135 for subbase. So I'm just assuming it's a base. Times E0 over ER, which is this one. Times exponential of minus 1 times rho over N.
Thousands, yeah.
Yes, but I wanted to play with the value, so I'm gonna put it like that. To the power of beta. Yeah, I think that's fine. Now, that's plastic strain, right? If I want see, like I did before, I wrote the deformation, right? So let's also have the deformation. So plastic deformation is gonna be, but I need the plastic strain, sorry. I'm missing the multiplication because it's EP over EV. So I need to multiply this still. I need to multiply it by the elastic strain. There. And now this plastic strain by the thickness will give me the deformation, and this is in inches. And if I want this in millimeters, This is millimeters. So if this is part of the same pavement system, when the base goes down because suffers a deformation, the asphalt will go that amount as well, plus the deformation of the asphalt. I'm not sure I'm illustrating myself. I have hot mix asphalt and I have the base. The base goes down this amount. The asphalt automatically goes down that amount because it's supported directly over the base. But the asphalt is also going down whatever this amount happens to be. Now, of course, this number of repetitions has to be tied with the same number of repetitions we had before. When I did this, I was doing it separately. But now, whatever number I put here will be the same as the number that I use for this one. It has to be the same number. But my asphalt will also suffer the deformation from here. Sorry, has to be negative. So truly, my asphalt is the accumulation of those two layers. So then again, 100,000 gives me 3 millimeters already because it's 2 in the base and 1.3 on the hot mix asphalt. Do you see what I'm saying, guys? You have to accumulate both of them.
So which means technically if you're accumulating everything, then the failure could be a lot earlier than or a lot less repetitions compared to 11 million, right?
Oh yes, exactly. Because before I was ignoring the fact that it's supported over a base. And if there's a sub base and the sub base is going down as well, just imagine that's the sub base. I'm just making up a number. And you also need to consider that in here, okay? So each layer will suffer a permanent deformation, and in the surface is the accumulation of all of them.
Yeah.
So it looks like this. This is the deformation on your subbase. This is the deformation on your base. This is the deformation on your asphalt cement. And this is your total deformation when you aggregate them all together. Please notice this is not the same scale, right? I might want to shrink this probably to avoid confusion. No, that it was correct there. I had it in a size almost right. Okay, so this plus this plus this sub-base plus base plus asphalt cement layer is the rutting that you experience on the top, on the surface, the one that you see on the pavement. But if you were able to dig, you will see that in the bottom of the hot mix asphalt, there is rutting. In the bottom of the base, there's rutting. And in the bottom of the sub-base, in the contact with the subgrade soil, there's also rutting.
But those two base and the sub-base curves are pretty, sort of.
It's because of this one. They look flat because of this one, because this is going aggressively high.
That's exponentially going up. Yeah.
They're not constant, but it's because this one is very aggressive. They're going up very slowly. I'm not sure
Okay.
if you can notice it.
Yeah.
But it's very slow. It's the asphalt that one that goes very aggressive. So which layer should you concentrate on then to design right if you don't want this to happen? I know
The
this is pavement
asphalt.
management. Exactly, the asphalt.
Yes. But sorry, Professor, why was the base? It's not start from zero base and asphalt. They shouldn't start from zero deformation
They're not
in the
starting
graph.
from zero.
Yeah, I mean they start from 0.1, for example.
They have a small value, but it's depending on the combinations that I have. So they have 0.08 rutting, while the asphalt has a big rutting. Probably I'm using, I'm using a 6 inches asphalt cement layer, very skinny. If I increase this, the rutting on the asphalt will go down, and now it's gonna look more considerable. See? Now the rutting on the base is more important than the rutting on the other one. It's because I use a very skinny layer here. The point is, guys, this rutting accumulates through the different layers. And the more repetitions we observe, the faster it will accumulate, okay? The repetitions are tied with time, as I was showing you before. And you have to consider the rutting in all the layers. Okay. So far we have seen the deflection basin area and the rutting and the cracking, right? And I want to recap here one thing. We can know when we need to do things just based on those three. For instance, I know that if my rutting is less than 13 millimeters, I can still do maintenance and rehabilitation of the pavement. I can still do maintenance, let's call it. But when the rutting is bigger than 13 millimeters, pavement is gone. Have to do reconstruction. Could be partial reconstruction or full reconstruction. The cracking is less than 20% on the wheel pad, and that means I can still do maintenance. The cracking is more than 20%, the pavement is gone. And there's even more than that, okay? But we're gonna talk about it. But this is why the rutting and the cracking are preferable indicators for pavement condition, because they actually tell you how much damage you have. We're gonna talk about roughness, but the roughness is an aggregated surface indicator that is really the quality of the ride. It was created in the 80s by the World Bank when they developed the Highway Design Manual 3, the HDM3. And it's based on a big equation. The one I'm showing you here is a simplified version of that equation. The complete equation will have plus and a bunch of terms that are related to the block cracking, top down, bottom up cracking, the rutting, and many other things. So it combines all the damage and comes up with this. You can always use the core of the equation where you have the number of load applications. So this is load cycles, the same we have been seeing before, 1,000, 11 million. And the structural number, which is the strength of the layer, which we covered before. So you divide those two, this to the power of 5. You have a coefficient here that is a calibration constant. You have the initial rutting in the moment of construction, which is typically like 1.8, sometimes 1.5 if the contractor is not very good. And you have M, which is a coefficient called Thorne-White moisture index. This is the amount of moisture by the climatic region. And then based on that, you establish the amount of roughness that you have. Now, this is the original formulation from the 1980s. So smooth ride, like the top image, is 0.5, 0.8. You don't feel your vehicle moving. It's super smooth. And this is how many vertical meters per kilometer you observe. Of course, the one on the right-hand side is a joke. You will not drive over that. But this is like the terminal state when the rutting, when the roughness goes to 80, 90, a very large number. We will typically have a value that goes somewhere between 1 and 10 maximum. There is a new way to estimate it that came with the Mechanistic Empirical Pavement Design Guide in 2006-2007. Is using the initial RI, but it's using a side factor. And the side factor combines some of the climatic information. Then you have the age of the pavement in the lifespan divided by 20. 20 is like the limiting factor. And see, you have here transverse cracks. And you have here fatigue cracking, the one we estimated before. And you have block cracking. And so you have your damage indicators. This side factor depends on the amount of rain. So this is the standard deviation of the rain. And this one over here, RM, is the mean, the average amount of rain in 1 year, in millimeters. And this is the standard deviation that accompanies the average. Your PI is the plastic index, plasticity index. The P0075 and the P002 is the subgrade particle that you do a testing on the lab with CIVS. And that will estimate your side factor. Side factor goes back and enters in this equation, and you can estimate some form of RI. Okay, so I'm gonna use this one just for now and make an example, okay? I'm gonna just see if I can make it bigger. Okay, so I'm using that. So we're gonna have the time, or if you prefer year. And so it's gonna be year 1, 2, 3, 4, 5, oops, 5, 6, 7, 8, okay? And I'm gonna have, let me estimate my structural number here. So it's gonna be hot mix asphalt layer base. So let's have 2 layers. So let's have the first layer, why not, 6 inches. And the second layer, 10 inches. I think that's the example we used before. And I'm gonna use coefficient A1 and A2. So I hope you trust me. I'm just gonna use 0.35 for this and 0.15 for that. Don't worry, I will probably give you the structural number at once. I just want you to see where this is coming. So I just multiply this times this and this times this, and I make a summation of this plus that. Oh. No, it's still too
Share, multiplying or add?
Multiplying. I added, sorry, that's my mistake. That's why it was not working.
Okay.
Thanks, thank you. So let's go back to the value we had before. Okay. So this is my structural number, Sn. That's the SNC, okay, so it's NCC. And then my results, let's put my results here. So let's imagine I have, I think I said 750,000 before in the example. And then I say a growth rate, let's imagine it's constant of 3%. So this will be 1.03 times that. And my results will grow. But I need to accumulate. So accumulated results. Well, at the beginning it's only that, but then it's gonna be the one before plus this one. And I'm just gonna change this to have no decimals. Okay, maybe I put a couple extra years, all the way to 10 years. And let's assume alpha, maybe 250. I know you don't know where this is coming from, guys, but this is things you need to calibrate. So it's not that easy, but trust me, that's a reasonable value. And what else do I need? I need M. So let's use 0.07 for this example. So this is the environment that is in there. And I'm just gonna extend this a bit so you can see the whole thing. And I'm gonna have my RI, which is gonna be equals to, and then it's EXP of M times the time times the RI0. Oh, I didn't write it, eh? Okay, I'm gonna assume RI0 is, okay, let me put it here. Let's assume it's 1.0. So those two values are together. That value is there. Okay, so I was saying this is exponential of M multiplied by time times my RI0 times alpha to the, and then I have the accumulated results divided by 1 plus the structural number, which is that one, 3.6. And all that is to the power of 5. That close that parenthesis. That is multiplying the alpha, and I close this parenthesis, and I think I'm good to go. No, that's not correct. Something is wrong here. What did I did wrong? Oh, everything is in the exponential, is it not? That's what I did wrong. No, the exponential is fine, it's there.
One more extra parenthesis.
Where, sorry guys. Yeah. No, where something is wrong here.
Or are you taking the power of 5 for everything? Maybe additional parentheses can help.
1 plus this, but this is for everything. This will be for, do you think it's doing it for everything?
But that's just for 1 plus structural number, right?
Yeah, it's 1 plus L3. So do you think like that? No?
No, no, it's still high.
Something is wrong here.
Can you put the exponential in different parentheses from the beginning of that to the very end of that?
Like this?
Yeah.
Same.
Okay. Do we have anything else after this, like the cumulative acyls and the structural factor in our formula?
No.
No, because we cannot see that. This is behind the Excel file.
No, see, it's here.
Can we break down maybe the first expression, the EXP E3 A3, and then calculate the other one separately?
Okay.
Sorry, for Sn, we didn't have to multiply m.
I'm assuming it's 1.
Okay.
What? No kidding. Oh, it doesn't want to take it. Okay, give me a second. Something happened here. Okay, no, but this is the one, right? So the one is going to be fixed.
Alpha.
Did I make a mistake with the alpha?
But the alpha is the same, regardless we make it constant or we use that formula, so it's going to be same. Is there anything else constant that we? The structural number?
Is 1 plus that. Okay. Let me open one that is done. Just a second. I'm just going to open one that is already done. No way. I thought I had one here handy. See, alpha is 265, so my alpha is not that far off. And my M, what am I using for M? 0.07, I have 0.06, but this is a sketchy one. And structural number coefficient is als RI time, so why it's not working?
In the formula, are we making the structural number constant?
No. I found it, Cameron, sorry.
Okay.
The ESALs are per million. The ESALs should enter in per million. Got it. Sorry, guys. It's been a while. These ESALs should be per million. I need to put this. This is in millions. I will post an updated of this lecture soon, okay? But it's in millions. So right now, I'm just taking the number by itself, so here. So here is, okay, where are my cells? Here. Yeah, so this cells is per million. It has to be per million. Now, what did I did wrong? Oh, this
Because
is
there's
not
no
arriving.
decimals. It has
Yeah,
two
yeah,
decimals.
it's not arriving to the 1 million. That's why.
Yeah.
Decimal. Okay, yeah, now it makes sense. Okay, now it makes sense. So now I can put this together with the other one. So it was this.
Multiply by the rest of them. Yeah,
Multiply by that.
exactly.
Yeah. And I just need to make sure that the cells are fixed. So D1 is fixed, correct? M3 is the structural number, that's fixed, correct? The year is changed, that's correct. The E is fixed really, but let it change, doesn't matter. The E cells will change and the D3 will change. So apparently should work. Yeah, correct, it's working. So it's moving from 117 to 225 after 10 years. So now, how do I know what to do on a pavement that is at 225? Is that good? Is that bad? Or if I continue here, more years. Now I reach 9 after 29 years. And for instance, I reach 40 at 3 after 14 years. But do you see the problem? This is meters on the vertical divided by kilometers on the horizontal. It's hard, it's difficult to know how to associate this with the different actions that I will do on a pavement. The reason why everybody use this is because there's a specific machine that goes out there and collect this information and prepare this, and it's standardized across the world. And because the World Bank also proposed this. Of course, there's people who will tell you if the pavement is bigger than 181, this is New Brunswick. This is a reconstruction. But if you go to my home country, Costa Rica, this is a reconstruction. So it's not the same. And other places like Quebec will probably tolerate 3 point something. Go ahead, you had a question, I think.
Yeah, this that you're explaining it means the different countries basically has different standards for the level of tolerance.
Correct.
Mm-hmm.
Correct. So it's a bit difficult to know. Of course, you can plot how this is going to move across time and then use it for your forecast. But it's preferable if you can plot the permanent deformation that you have here after your repetitions, because this is the results. So just as I have 750,000 there, and then at some point here, where is it? At this point that New Brunswick has failure, I have accumulated oh, this is accumulating. Hold on, guys.
Accumulated, but in millions.
No.
Check the bottom part of that, the next cell.
I lost the accumulation. This is correct for the first one, but the second one was accumulating and I lost the accumulation.
Uh-huh.
This one should take this plus, so this times 1 million.
Or maybe create another column for accumulated and then convert to millions.
Yeah, that looks about right now. That's why it was going so slow. So here, Quebec will do reconstruction here. Okay. So you have 6.67 million. How much is that in Rutting? Maybe it's sufficient. I don't know. Yes, it is. You see, 11.89, but just by coincidence right now. And if you go into the other one that was cracking, that much, right? But this is, where am I reading my damage? So this has not reached. What is 66 over 32 million? It's at 20%. Okay, this is making me look bad because it's matching. But that means Quebec has made a good job at recognizing. Okay, are you guys following me?
Yes.
I say that this is my reconstruction criteria, right?
Yes.
Then I'm probably about right. Because in terms of cracking is at 20% and in terms of rutting is 13 millimeters. So this is my total rutting, all layers. And this is my total here. So I'm getting to 12. You see? And I need 13, so I'm close to that.
Yeah.
And in cracking, I'm at 20% fatigue damage. So fatigue cracking will be, sorry guys, it's going to go here. Fatigue cracking is given by this equation. So it's 10,560 divided over 1 plus exponential of 7 minus 3.5 times the logarithm of this one over here. Oh, I might need to put that in a number, not in a percentage, I think.
Just write it down.
This is incorrect. There's something wrong in the calculation. Okay, just ignore.
Change 20% to 0.2 maybe. Does that help?
That's what I try to put it as 0.2.
No, you have to change the format to decimals.
Okay. Yeah. I don't know if I should enter in percentage, but it's not gonna. I need to check, guys. I need to check the units. For now, I know when I prepared the chart, this one was, so if I'm at a 20% for a 6 inches, I should be like at a 10% cracking, and that's not what that is giving me. So maybe I should go in that. No, going too far. Okay, just ignore that. This is a 10%, a 20% damage. And will give me a corresponding value here of cracking. But the point is, for these indicators, for cracking and for rutting, the values are clear. You can get a percentage there, or you can get a millimeters here. And you know when you need to do repairs. But here in roughness is a little difficult, really. And as I said, in Costa Rica, they are using this. So this will be 11.71 million. So that means they have here 11.710. So they already went beyond the maximum rutting. They are tolerating beyond what the asphalt, the AASHTO is suggesting you should tolerate. And of course, if we go to cracking, this is not tie, but I say how many? 11.7, right?
Yes, exactly.
So you are at 36% damage. So they are tolerating further damage. So it's not that easy just by this number to know. Of course, we can do it now because we have this calculator, although it looks like I'm a bit tired today, so I'm not getting the numbers right. But I hope you understand what I'm doing. The point is, you don't have this. Typically, you only have this, RI. And you cannot see this rutting millimeters, and you cannot see this fatigue damage percentage or area. You can only see this. So that's why it's difficult. Now, the final one is the pavement condition index. And this one is even worse, because for this one, you will take anything that you have and you will combine it to produce an overall measure of the pavement quality. So I'm showing an example there, but I can show you a different example if you want. I could combine the RI and the deflection basin. In this case, I'm showing here, I'm combining the rutting and the cracking. And when I combine those two, I obtain specific values. So pavement condition index, although sounds nice, and you have heard about this many times, you keep on hearing this because this is what everybody used to communicate to the public at large. It's not something we use to make decisions, because I could have different combinations and this can give me different pavement condition index. So for instance, imagine I have, I'll just take this one. So the first one is rutting, millimeters. The second one is crack area in percentage. And the last one is deflection basin area from 11 to 36, okay, as it is written there. And we're gonna use this equation to estimate PCI. So I have rutting 0.5 times 100 minus the rutting divided by 13. You see how 13 is my limiting criteria, right? 13 millimeters, that's where that is coming from. And I am increasing that by the crack area in percentage. And then I'm adding another 50% that is coming from 100 times the dBA minus 11, which is the minimum, divided by 25. Okay, so apparently it's correct. So we will say the higher the value, the better the condition of the pavement. The lower the value, the worse the condition of the pavement. So you will say 86 is very good. 66 is fair, maybe. 44 is bad or poor value. And 27 is very poor, if you wish. But if I only have this and I don't have the rest, so the rest is hidden to me, then I don't know what type of repair I need to do on the pavement by looking at the PCI. For instance, let's imagine the rutting is 20. But the crack area is very low. And the deflection basin area is that. I still get the 86. But my rutting of 20 means that I have a lot of rutting. You see? Or maybe my rutting is very good. 5, I have very little. And I have a 35% of the area crack. But the pavement is strong and it still shows a high value. Do you see the problem, guys?
Yes.
It is only when the deflection basin area goes down that the value will go down. So if the deflectionary basin goes to 18, the value will go down. And now maybe I have 1% crack area and 1 millimeter in rutting. My deflection basin area is 16 or 14. So it's only this one because of the weight that I have used and the approach that I have used to combine it. So this impedes to identify the repair that is needed. Because if you are in this circumstance, you can see the DBI and you know you need to do some structural intervention. On the surface, the pavement looks brand new. No rutting and no crack. I can even put a 0 there if you want. But I don't see that. All I see is a pavement in good condition and the PCI will look a little low and suspicious. Imagine my PCI is maybe 18. It doesn't look even that bad. Now imagine I have a strong pavement, but my rutting is high. It's still looking the same. It doesn't matter. It's not being that much affected by these values. Start being affected by those values when these start going down. Then this value start playing a role.
Can I ask a question?
Yes.
So you mean by having only PCI, we cannot basically assess our pavement?
Correct.
Mm-hmm.
You cannot make decisions.
Yeah.
But that's, however, the favorite way for countries to report values.
Mm-hmm.
Online, that's what you're gonna come across.
But when they report the values, the pavement condition index values, do they give the full picture of, as in how much rutting we are getting and how much cracking area we are getting, or just
they hide
just report the PCI?
That this is hidden.
So how do engineers make the decisions then?
Oh, engineers require this. You need this. You need the detailed indicators, rutting, cracking, and deflection basin area.
Okay, but just for public, it's mainly the PCI that, because they sort of, for a layman, I mean, it's easy to understand. Okay, pavement condition, yeah, higher the number, better the pavement, right?
Yes.
So technically, which means that both the roughness index and the condition index, I mean, without the background information, I mean, they don't really mean anything.
That's correct.
Right?
The roughness is a little better because it's like an accumulation of everything. So at least in roughness, you know that is the accumulation of everything together and is amount of vertical variation. I don't know if there's a video for roughness.
Yeah.
Hi, Professor. I want to ask, with regards to IRI, we know it's the vertical displacement over a certain kilometer, right? So now we are using an equation to determine this roughness, whereby probably on the field, the situation might be different. So like, do you have a particular equipment where we can drive on the road